Hi, this is Dr. S.P. Harsa from Mechanical and Industrial Engineering Department, IT Roorkee. I am going to deliver today my lecture 7 of this title of the strength of materials, in which we are going to discuss about some of the problems. As if you refresh the previous lectures, the last two lectures were discussed about the various stress components and what the distribution is there of these stresses when the load applications are there of either the single or the mutual kind. As you see, actually in my lecture 5 we discussed about the analytical solution when you see when a material is being subjected by a pure normal stress, the normal forces, or a material is subjected by pure this shear loads are there, or we can say when it is under the normal stress components are there, or pure shear stresses are there, or when a material is subjected by the two mutually perpendicular the stress components like sigma x and sigma y, and the same time simultaneously we can say that if the shear stress is there, then what exactly the the interaction is there of these stresses, and what exactly the impact of these stresses on the material. And through the analysis we can also find it out that actually how to get the maximum value of the normal stress component, or how to get the maximum value of the shear stress component by analytically. We discussed all those things. So if you just remind, then actually just I want to refresh those things, that actually if we have a material which is being subjected under two mutually perpendicular stresses like sigma x and sigma y, and also the same time there is a shear stress is there along the plane, because it's a parallel to the layers of the surfaces. So if the shear stress is there which is tending to move towards the clockwise direction, and the simultaneously see to balance this material, we always need the complementary shear stresses, the Q dash. So that means we can say that if a material is subjected under the combination of these three components sigma x, sigma y, and the tau xy, then we can also find it out that actually what exactly the stress component is there at any angle. We can say at oblique plane, which is at angle of theta. We can calculate, like let us say if it is at the angle of theta, we can say the normal stress component as well as the shear stress component at the theta we can easily calculate by analytical technique, like sigma theta is nothing but equals to tau x plus tau y by 2 plus sigma x minus sigma y by 2 cos of 2 theta plus tau xy by 2 sine of 2 theta. So this is, you see, the normal stress component if all combination is there, means all three combination is there of this stress component. And also we can calculate the tau theta, that is nothing but equals to tau x sigma x minus sigma y by 2 plus plus half of square root of sigma x minus sigma y whole square plus 4 times of tau square xy. Means, you see, we can easily calculate that what the stress distribution is there, and if you want to calculate the maximum normal stress component within this object, if it is under the application of these three mutually perpendicular stresses, we can also calculate, you see, by simply differentiating sigma the sigma theta by d theta, putting equals to 0, we know that what is the location, that is tan 2 theta p, which is nothing but equals to 2 times of tau xy divided by sigma x minus sigma y. And also if you keep those things there in the mean value, you can get the maximum value or minimum value of the normal stress component, that is sigma 1 comma sigma 2, which is nothing but equals to sigma x plus sigma y by 2 plus minus square root of sigma x minus sigma y whole square plus 4 times of tau square xy. That means, you see, you have two the values of these things. One is the maximum value when you are choosing plus sign. If you are when you are using minus sign, that means it has a minimum value. The meaning is that, you see, these two value sigma 1 and sigma 2 are nothing but the principal stresses, and also we can say that these stresses are always occurring at the planes, and these planes are known as the principal planes. Then we conclude that actually if you want to calculate where these what is the value of the shear stress, if we have the maximum normal stress is there, we found that the value of the shear stress is 0. So we concluded that actually always the maximum normal stresses are occurring in a in a material always where the shear stress is 0. That means, you see, the principal stresses are always one can get if the shear stress value is 0, or we can say wherever the shear stress, these principal stresses are occurring in the object, these planes are known as the principal planes. And if you want to locate those principal planes, one can easily put the shear stress 0, get the value, and you can simply locate the theta p. And also we relate that if the maximum shear stress is there, then what is the tan 2 theta is there. So we calculate that tan 2 theta s is nothing but equals to sigma x minus sigma minus times of sigma x minus sigma y divided by 4 times of this tau xy. So you see we have a mutually like perpendicular, or I should say that we have a reciprocal relations between the tan to theta p and tan to theta s. So that's what you see like we discussed about the analytical solution of any problem which is like under the subject of variety of these stresses. Then other solution which we discussed about the Mohr circle, that is the graphical solution. So in that also you see we are going to use all those analytical part which we have used in like for solving those things. That means if a material is subjected under the same pure normal stress, pure shear stress, or two mutually perpendicular like the normal stress with the shear stress, then you see like how to draw the Mohr circle, what will be the center, the coordinate of the center point, what will be the radius of that. And you see on x axis, as you discussed that on x axis we are taking the normal stress component, on y axis we are taking the shear stress component, and then how to plot that part, what will be the like the center distance is there right from the origin to this part, or what will be the maximum you see the diameter is there, how to like put the, if you want to calculate the this the shear stress or the normal stress at the oblique plane, then how to like put the 2 theta, or we can say what will be the relation between the beta and theta. So all the sorts of things you see we discussed in the lecture 6. So today is lecture 7. So whatever we discussed in lecture 5 about the analytical solution, in lecture 6 about the graphical solution, today you see we are gonna merge those things like, and we just want to apply in a real practical phenomena, that is the numerical problems. And you see today we are going to discuss about both the solution for an specific problem. So the first problem we are going to discuss about the two problem. The first problem is pretty simple problem, okay, and the second problem you see like somewhat more complex problem is there. So we just want to generalize that problem, we just want to find it out the state this general state of stress, like the what will be the value of these things, like of the general state of stress if it is subjected under these kind of loadings. So you see this kind of like the phenomena which we are going to discuss in this lecture. So here it is, you see we have like the first problem. So you see this chapter itself, the name is illustrative problems, and you see we are going to discuss a few representative problem dealing with the complex state of stress which has to be solved either analytically or graphically. Okay, so you see here we are going to apply whatever we discussed in the chapter lecture 7 or lecture 5 and lecture 6. So here the statement of the problem 1, which is a circular bar, we have a circular bar of the diameter is 40 mm, like carries an axial tensile load of 105 kilonewton. Means you see we have a kind of bar which has a diameter of 40 mm, or we can say the 4 centimeter dia like a pencil, and there is a Newton which is like there is a load which is applying on the just two extreme ends, which is the nature of the load is axial pulling. So when you are pulling, you see like there is a tendency of a material to resist that thing as per the Newton's third law. So what will happen once you see like the load application is there, the internal like the load distribution is like that, and if you are saying that the action whatever you see by 105 kilonewton and the reaction you see just to resist that force, if they are well maintained, we can say that this the system is under equilibrium position. So whatever the stresses which are being set up within the structure, these stresses are the tensile stresses because of the axial pulling. So now you see like we have this load, we have the diameter of this like the circular bar. So what we can do now, we can simply calculate the tensile stress. But you see here the other information is given, the what is the value of the shear stress. We need to find out the shear stress value just by applying the load of tensile on a planes on which the normal stress has a value of 50 meganewton per meter square tensile. Means that you see like we just want to cut the plane at a certain like angle, we do not know the angle, but you see at that particular like at this particular plane we have a normal stress component, that is the sigma theta, which is 50 meganewton per meter square, and we just want to find it out that what will be the value of tau theta at this particular plane. So now you see the solution, just as we discussed, it is a tensile loading, so we can simply calculate the tensile stress, and tensile stress is nothing but equals to the applied load, the applied tensile load divided by the effective area. And since it is a circular bar, so effective area is pi by 4 d square or pi r square, and you see here we have the diameter is 40 mm, we can say it is a 20 mm radius is there. So 105 into 10 to the power cube, that is the applied load, divided by pi into 0.02 square. So you see you can calculate the tensile stress, which is nothing but equals to the 83.55 meganewton per meter square. Now you see the other information was given that we have a normal stress like at an oblique plane which is equals to 50 meganewton per meter square. But you see by the formula, when a material or you see any object, if it is subjected by a pure tensile load, then the normal stress component is nothing but equals to the applied stress into sin square theta. So here you see here, if we apply the concept, then we have the sigma theta, which is the stress at an oblique plane, normal stress component is equal to the applied stress at the extreme end, that is sigma y into sin square theta. But we don't know what is the angle of the normal plane is, means actually where the oblique plane is cutting at that particular point. So we would like to know these things. So you see, if we put all those values, means the sigma theta is nothing but equals to 50 into 10 to the power 6, which is equals to sigma y is nothing but equal to 83.55 meganewton per meter square into 10 to the power 6, because you see, we just want to equate those things into sin square theta. So once we put all those values, we can simply calculate the sin square theta has some value, because if you put all those things at this particular side of the equation, we have sin square theta equals to some value, and once you square root those things and put the inverse sign, you have the angle, means at what angle this oblique plane is there, and at the oblique plane at this particular 50 degree in 50.68 degree, we have the value of the stress is 50 meganewton per meter square. So now you see, we know the location. Once you know the location, you can easily get what is the value of the shear stress is. So you see, if you move further, then you will find that the shear stress at this particular plane, where the theta is theta is 50.68 is. Now you see, this theta is for the normal stress component, because you see it is there. So if you want to calculate the shear stress part, then what we need to do, we need to simply keep that particular theta in a real formula. So you see, for tau theta, the standard formula when a material is subjected by a pure tensile load, the formula says that the tau theta should be calculated by sigma y, which is the applied stress, into sin 2 theta divided by 2. So once we apply this formula, now we can get this value of tau theta, which is half of sigma y, which is 83.55 meganewton per meter square. So into 10 to the power 6 into sin 2 theta, and the theta was 50 point, if you see the previous slide, then we have 50.68. So if you multiply by 2, then we have this value. So we can simply put sign of 101.36. So we can calculate the tau theta, which is equals to 40.96 meganewton per meter square. So here you see, these stress components, either the sigma theta or tau theta, one can easily calculate if you know the formula, or if you see what the stress distribution is there under the application of any load. So here you see this, the example was a pretty simple example, and this example just gives you the information that actually even if a material is subjected by a pure normal stress, in this particular microstructure, or the structural part of the element is always carrying the normal stress component as well as the shear stress component. So you can simply compare that we have, you see, the magnitude of the tensile stress is 83.55, but also you see, apart from that, we have both the component at an oblique plane. We have, you see, the sigma theta, which has a value of 50 meganewton per meter square, and we have the value of the shear stress at the oblique plane, that is equals to 40.96 meganewton per meter square. So you see actually how to calculate what is the physical significance. That's what we calculate here. Now come to the second problem. Second problem is somewhat I should say the mixed nature, because you see here not only the tensile loading is there, but also apart from the tensile loading, we have the shear loading here. So here the statement of the problem is, for a given loading conditions, the state of stress in a wall of cylindrical the thing. So means now you see our object is cylinder, and in the cylinder you see we would like to see that actually what exactly the coordinate system is, and how we can correlate with the stress component is. So here the wall of a cylinder is expressed as follows. Here you see, the first loading is tensile loading. So first part 85 meganewton per meter square tensile loading is there. Then B part says that 25 meganewton per meter square tensile at right angle to A. Means you see, wherever this tensile loading is there, if you consider that this tensile loading is in x direction, because it's a normal stress component, tensile is there, okay. So if we are considering that this is in the x direction, then the other component, which is of 25 meganewton per meter square, is also having the tensile nature, but it is exactly right angle to this. Means say that if I am saying that this here you see on this on an element, if this is my direction which gives you the 85 mega Newton per meter square in this direction, means this this tensile direction, then you see the 25 mega Newton per meter square, like the other loading is there, is always in the right angle to the this particular the previous one, and it is also in the tensile loading. So you see here, this is the correct like the physical description about these two, A and B. And the third thing is that the shear stress is there, which is a parallel like the plane stress. That means it has a parallel concept to the this layers of the object, or we can say the cylinder. So shear stress of 60 mega Newton per meter square on the planes on which the stress A and B acts, you see here. So that means the shear planes, like it is in the like as I told you, these normal stress components or the normal stresses are the axial stresses, while the shear stress is a plane stress. So now it is along a plane where these two above stresses are acting. Okay, so means you see at one point of time I can say that here 85 mega Newton per meter square is acting, at this point this 25 mega Newton per meter square is acting, and along this plane means the shearing part, you see here this 60 mega Newton per meter square is acting, and then you see the shear couple, whatever the shear couple is there, acting on a planes carrying 25 mega newtons like the stress in a clockwise direction, you see, meaning that you see wherever if I am considering the 25 mega Newton per meter square, the B part on the top of side, so and the top of side you see I have the shear stress, means actually the shear stress is occurring on a plane where our vertical direction, I should say the 25 mega Newton per meter square stress is acting. So both are acting on a same plane, one is a normal, one is a parallel. So this shear stress component is always combining with the 25 mega Newton per meter square, but the direction is always this shear stress is directed towards a clockwise direction as it is. So you see here, as far as if you go to the convention, real convention, we say always like we said that if it is a tensile stress component, then it is, you see, the positive direction, you need to take the sign convention as positive. And also if the shear stress, because of the induction effect of the shear stress, if object is tending to move towards a clockwise direction, always take positive. So here you see here I have now the complete configuration of the this problem is we have two stresses perpendicular to each other, 85, 25, and we have the 60 mega Newton shear stress, which just try to like tend this cylindrical object into the clockwise direction. So this is, you see, the clockwise direction. So you see the anti-clockwise like the complementary shear stress will come just to balance the condition. So now if we now the calculative part is calculate the principal stresses, because you see now all three combination of, or we can say all three types of the stresses are there. So we need to calculate what will be the sigma 1 value and sigma 2 value, the minimum and maximum principal stresses. Also the and the plane, that what is the principal planes are there, means what is the location of the principal plane at which they are acting, all three components, and what would be the effect on these results if owing to a change of loading A becomes compressive. Means you see just now you see in the first case what we are taking that the first case means 85 mega Newton per meter square, the load is a tensile load. Now if I reverse this, means you see now I have a compressive load of 80, the same magnitude, that means the 85 mega Newton per meter square, then what will happen? While the stress B and C remains same, means you see the B is always going the tensile 25 mega Newton per meter square, and the C means the shear stress is just tending to move the this object towards the clockwise direction. So it has a value of 60 mega Newton per meter square. So now this is the complete problem, so we can simply calculate either by analytical solution or by graphical solution. So now you see here the solution is, so as I discussed, you see already that actually what is the physical the phenomena of this problem is, the problem may be attempted both analytical as well as graphical. So here you see first we will go with the analytical solution. So here the problem is we have a cylindrical part, we just taken a small element which is symmetrical in all the 6 directions. So it is a kind of a unit cube in which which has a unit width, the width, unit depth, and unit breadth is there. So now on these the axial stresses are the sigma x, which the tensile nature, so it is of 85 mega Newton per meter square, perpendicular to that, that is this one sigma y, that is 25 meganewton per meter square, and the shear stress, you see these are the shear stress component which always try to tend this object in the clockwise direction, and it has a value of 60 meganewton per meter square, and it is only acting where this 25 meganewton per meter square is. So this is, you see, the active plane where the perpendicular stresses are there, where the parallel stresses are there. So the meaning is, this is the complete configuration of the problem which, you know, like which has, you know, like written in the previous slides. So this is, you see, the graphical this description of a problem in a perfect way. So you see here, now come to the real formula which we discussed in the, you know, like the 6th chapter, that the analytical solution always gives you the value of the principal stresses where the shear stress is 0, or we can say we can simply calculate the sigma 1 and sigma 2 value if you know the value of sigma x, sigma y and tau xy. So all the values are given to us: sigma x 85, you know, like meganewton per meter square, sigma y that is 25, you know, like meganewton per meter square, and both are tensile nature. So we have to take the positive sign for that, and the tau xy which is 60 meganewton per meter square, and it is also tending to move this particular object in the clockwise direction, so it is also positive. That means, you see, all three values are given to us, they are positive, so we need to put the positive value, and you see, you know, like we can simply calculate, if you know the formula sigma 1 and sigma 2, these are the two principal stresses, maximum and minimum, just by keeping plus minus sign. So here it is, the formula is sigma x plus sigma y by 2 plus minus half of sigma x minus sigma y, you know, like whole square plus 4 times of tau square xy. So by keeping those things, we have the 85, that is sigma x, plus you see the 25, that is sigma y, plus minus half square root of the sigma x value is 85 plus sigma y, that is 25 whole square plus 4 times of 60, that is the tau xy square 60 square. So if you calculate those things, then we have, you see, like this 85 plus 25 if divided by 2, then we have the 55 plus minus half of, you know, like this 60 into square root of 5. So once you calculate those things, you have two values, 55 plus minus 67, means, you see, we have the maximum value of the principal stress is 122 meganewton per meter square. We have the minimum value of principal stress, that is minus 12 meganewton per meter square, and since it is a minus, so it has a compressive nature. The first principal stress, which is a positive, so it has a tensile nature. Meaning is that, you know, like you can pretty simply, you know, like calculate those things once you know the values of sigma x, sigma y and tau xy, plus if you know the sign convention, that actually what is the point of application of the force is, means how these forces are acting, and due to these forces what types of stresses are inducing, means the tensile nature, compressive nature, you know, like shear stress is there, then what is the complementary shear stress is there, whether it is tending towards the clockwise direction or counterclockwise direction. So these, you know, like two important points are there, that what the information is given to us, means what kind of stress components are there, or what the material is under what types of stresses, and the second part, which is more important than actually that what the sign convention is, means actually how these stresses are being, you know, like set up within the object. So for finding out the planes on which the principal stresses are acting, it's pretty simple. You see, we can get the tan 2 theta is nothing but equals to 2 times of tau xy divided by sigma x minus sigma y. So we know the sigma x value, we know the sigma y value, we know the tau xy value, and all are positive. So we can simply keep those things, you know, like here the 2 times of 60 divided by 85 minus 25. So once you put those all three values, the solution of the equation, you can get the two values, because you see, you know, like the plus minus sign is there of this here, the tan inverse of that. So if you take the plus sign, then you have the theta 1, that is 31.71 degree, means, you see, you know, like if you tilt, like you see right now this cylindrical object is there, the previously which I shown you, you know, like if you tilt by 31 degree, then you see whatever the planes are coming, these planes are the principal planes, and whatever the stresses are there, like the sigma 1, that is in the tensile nature, and the magnitude is 122 meganewton per meter square, and the compressive stresses, that is, you see, you know, like the principal stresses 2, which is in this direction, the compressive one, means directed towards the element which has you know, like the value of this 12 meganewton per meter square, you can also calculate, you see the theta 2 value, that is just by adding 90 degree, because both are perpendicular to each other, because the mutually perpendicular stresses are there. So the theta 1 is 31.71 degree and theta 2 is just 31.71 degree plus 90 degree, that means the 121.71 degree. So you see here, first in this case now, the second part which we discussed, that actually if we reverse the loading of part A, as in the x direction, earlier we had taken the 85 meganewton per meter square in the tensile part. So now in this part, you see we can found that now it's a compressive one, because earlier it was the tensile, so compressive stresses are there. So you can see here 85 meganewton per meter square in the compressive way, and other stress components are pretty similar to the part A. Like you see here, we have the tensile stresses in the vertical direction, that is the 25 meganewton per meter square, and we have the shear stress component, that is 60 meganewton square, which is going towards the clockwise direction. So while you see the other stress, as we discussed those things, so now we want to analyze those things by analytical solution. So again you see would like to go with the sigma 1 and sigma 2 by the same formula, just the difference is sigma x is 85 minus, because it is a compressive one, so it will contains the negative sign. Otherwise you see other two stress component, because the on y direction we have the 25 meganewton per meter square, that is in the tensile nature, and the shear stress, that is tau xy, that is the which has a value of 60 meganewton per meter square, is the clockwise direction. So by keeping those values here, sigma 1 and sigma 2, we have half of sigma x plus sigma y, plus minus half of square root of sigma x minus sigma y whole square plus 4 times of tau square xy. So by keeping these things, we have the value minus 85 plus 25, these values sigma x and sigma y divided by 2, plus minus this half comes out, square root of minus 85 for sigma x, 25 for sigma y, plus 4 times of 60 for tau square xy, so 60 square is there. So if we are keeping these values, what we have the two the equations, minus 30 because of this, minus 85 plus 25, plus minus the 81.4. So now you have two values, the first value which is sigma 1, that is the 51.4 meganewton per meter square, and you have the sigma 2, that is the minus 111.4 meganewton per meter square. That means you see again the two principal stresses, one is in tensile nature with the magnitude of 51.4 meganewton per meter square, another principal stress which has you see the magnitude is 111.4 meganewton per meter square, but in the compressive nature. So these two you see now we can simply put those values to get what exactly the angle is there. So again for finding out that actually what the angle is there, to get the normal the oblique plane, simply or we can say the principal plane, that where exactly the principal planes are there, or where the shear stress value is 0, we can again go for the same formula which we applied in the previous case, tan 2 theta is equals to 2 times of tau xy divided by sigma x minus sigma y. So just you see we need to keep the values of 2 times of 60 divided by the sigma x, which is minus 85 minus 25. So we have the value of minus 12 by 11, or if we are keeping that value 2 theta is tan inverse of minus of 12 by 11, or we can say we have the value of theta is minus 23.74 degree. Means now you see we have the location of just minus means if we are going towards the right direction, we have these kind of values. So just you see we want to plot those things, the two principal stresses acting on two mutually perpendicular planes, always you see sigma x and sigma y is always acting at two mutually perpendicular planes, and those planes are the principal planes. Here you see, and we can easily depict it on the element as like here. So we have the pretty simple element which has all those three types of stresses, sigma x in this direction, sigma y in this direction, tau xy in this direction. It is equivalent to this direction. You see this is my reference plane, that is the BC plane. If you rotate this by the theta as we calculate in the first case, you see theta by this, you have sigma 1. So this is the sigma 1, you see in this direction sigma 1 is there, this direction gives you the sigma 2, and you see this is the first plane theta, the another plane, that was, you see, like if you just remind that the previous case we discussed about the theta 1, and then you see we added the theta for theta 2, we added the 90 degree. So this is, you see, the location of the another plane. So this is my principal plane 1, this is my principal plane 2. On these, you see, we have both the components sigma 1 and sigma 2, which is reference to this particular like plane. So this is my reference plane BC, or which we can simply rotate that part. So the location of the first principal stress, that is sigma theta 1, and corresponding sigma 1, which is pretty like easily calculated, and once you can plot the sigma 1 and this like the theta 1 on the oblique plane, what you can easily get like the other direction, that is, you see, other direction is nothing but the perpendicular to the previous one, that is sigma 2 a is always acting at the 90 degree of the previous one. Theta 1 plus 90 degree will give you the another location of the principal plane. So here you see like we have the two mutually perpendicular planes, so hence we can simply rotate the like the first plane by 90 degree to get the another plane direction. So now you see we can simply like complete all those things with, if you see the positive angles are there. But if you see, if theta is negative, that means, you see, we are measuring the angle in the opposite direction, means we are going towards the like another direction of the reference plane BC. Means right now you see the theta was positive, so what we are doing here, we are simply going towards this direction. Okay, this is BC, and this was, you see, the first principal plane is there, the location of this theta. Now if I am saying that in the second case, where you see we found that when this tensile stresses was negative, we found that the theta 1 was negative, means, you see, what we need to do, we need to locate this theta now by this reference plane to that direction. So theta 1 will go in that direction, then you need to add plus 90 to get the another location. So here it is, you see, this is my reference plane, as I discussed, BC kind of that. If theta is positive, then you need to go the positive direction here. If it is negative, then you need to go by minus theta. So this is the negative direction, and this is, once you have this, so this is my direction of the principal plane 1. And once you have the theta 1, to get the another value of theta 2, you need to add 90 degree. So here it is, you see, therefore the direction of the another principal plane would be minus theta plus 90, means what you need to do, just you put the minus theta is always less than, you see, whatever the magnitude is there, and you need to go in the other direction by adding 90 degree. Hence the quantity is minus theta plus 90 would be positive, therefore the inclination of other plane with the reference plane would be positive, because we are adding the 90 degree here, therefore it just complete the block, because we just want to complete the total block, but just by rotating, you see, like by adding the 90 degree in the minus theta, and it would appear as exactly like that. You see here, if it is minus theta, so you see this is my reference plane, it would be here minus theta, this is 1, so this is my first reference plane. Now what we need to do, we need to add those things. So this is, you see, the another reference plane which is coming by minus theta plus 90 degrees. So this is my sigma 2, sigma 1 is this. Okay, so this is, you see, the just to complete the block, what we need to do, we need to first put the minus theta here and minus theta plus 90 here. So this one is, like just gives you a clear picture about that if we have our theta is minus or theta is positive, we can simply rather to go like in positive direction or in negative direction here on the just two sides of the reference plane. If we just want to measure the angle from the reference plane, then you see you need to rotate the just block, because you see like what we need to do here, we just want to measure those angles, that actually if it is in the minus sign or in the positive sign, then how it appears. So what we need to here, just rotate the block by 180 degrees so as to have the following appearance. So what we did here, this is my reference plane, now this one is my like the theta, and this is whatever the theta angle is there at which you see this sigma 2 is acting, and this is the plane where just 90 degrees there, theta 2 plus 90. So this is my sigma 1. Meaning is pretty simple. If you want to appear those stresses, if it is minus theta or positive theta, and if you feel that the things are pretty complex, then what you need to do, you need to simply make like the block in such a way that either by rotating 90 or 180 degree, just to make the simplest way to represent those principal planes sigma this theta 1 and theta 2 at both the, you see, sigma 1 sigma 2 stresses are there. So whatever one of like whenever one of the angle comes negative like minus theta, as we discussed in the previous case, to get the positive value, first you need to add the 90 degree like just to get the positive value, and then another 90 degree to rotate the just to locate the another principal plane. Means pretty simple. If we have, let us say, minus like this one, in this case we have the first thing, theta is minus 23.74 degree. So you see it is like either to rotate this side rather to go in that direction, what we need to do, you need to simply add to locate the first principal plane, just adding 90. So you see here minus 23.74 plus 90 is 66.26 degree. So this is, you see, the location for first principal plane. Again, by adding 90 degree will give you the direction of the another principal plane, means you see again you need to add. So that's what you see in the previous slide. We discussed that actually if the things are pretty complex, what you need to do, you need to add 180 degree in total, 90 degree to just give the positive value and 90 degree to rotate that like the whole first principal plane to go to the second principal plane. So here you see we have the theta 2, that is the 66.26 degree plus 90, that is 156.26 degree. This is how you see we can show the angular position of these planes clearly, because you see if there is no ambiguity in that, if minus there you need to go like that, if it is a plus, theta 1 is plus. So you see just by adding 90 degree you can get like the location of the another principal plane. Now you see this was all about the analytical solution. So now come to the graphical solution. Like the graphical solution just gives you like you don't have to calculate all these plus, minus, theta, sigma, theta, tau, theta, all those like what the maximum and minimum values. Straight away you have the problem, plot those problems, get like just by measuring the other terms in the Mohr circle you can get exactly the solution is. So here you see comes to the main problem. Again the same problem is there, only the solution this variety of the solution is there. So solution way is different. Mohr circle solution, the same problem which we are taken, the two like the tensile stresses are there. The first is 85 meganewton per meter square, second one is 25 meganewton per meter square. Both are mutually perpendicular, one is along the x axis, one is along the y axis, and this material is under like the clockwise direction rotating under the effect of the shear stress, and the value of the shear stress is 60 meganewton per meter square. So this is the problem. Then construct the graphical construction. First you see we need to construct the graphical just by like putting all those formulae. So here what we have sigma 1, that is you see right from this to this we have the sigma 1. So all these things you see like can be easily calculated. This is my O point. From that you see we can get the sigma 2, that is the sigma 2. So O to this part is sigma 2, O to this part is my sigma 1, this one is my sigma 1. So once you have sigma 1 and sigma 2, we can simply get those values. Then you see this is my center point, we can get also the center point coordinates. This is my direct, you see the this diameter. So through this you see if you know the 2 theta, then we simply put this particular, simply rotate this by 2 theta, get this AB bar to BC bar as a diameter, and then once you have these things then we can simply get this radius. Or you see by simply giving the interception from these two AB2 or BC2 on the x axis, what we have the tau xy. So this tau xy is there, you see the sigma 1, sigma 2 we can simply get from the sigma x and sigma y. So these you see the Mohr circle, as we discussed that actually like it is always in between the sigma x axis, tau y axis. You can draw these things, and by measuring, now we can simply measure the required values. By measuring, you see by taking the measurement of the Mohr stress circle, the various quantities can be computed easily. Like sigma 1 is 120 meganewton per meter square, that is in the tensile nature, because you see it is in the positive direction. Just go back, you see like it is in the towards, you see horizon to this direction, so it is the positive direction, and you see the sigma 2 which is horizon to towards the left direction, so it is in the compressive nature, and it has a value of 10 because it's a very closest to the horizon, so 10 meganewton per meter square. And again you see because the 2 theta is there for AB bar to BC bar, you can again calculate the theta 1, that is the 34 degrees, the positive direction is there because of the clockwise from the BC, and then you see theta 2 is always coming by adding the 90 degree for the next principal plane location. So 34 degree plus 90 degrees 124 counterclockwise from the BC. So these values can easily, you see you don't have to calculate those things, you see that what is the value of the sigma x, sigma y, tau xy, sigma theta, tau theta, all those things. Straight away plot those things, sigma x, sigma y, tau xy, with the using of this information, plot the curve Mohr circle and get those values by measuring those things. So the part 2 in which you see the tau xy, the sigma x was the compressive one. You see the problem here in this slide, you see this is my like the square element, this sigma x is the compressive one, sigma y is like the tensile one, that is 25, this is 85, and this is 60 in the clockwise direction. So now you see keeping by these things like put those values sigma x, sigma y and get these. You see this is my main center coordinate through which you see this is passing. So what we need to do here, this is my sigma tau. So we have 2 theta, like we calculate the theta, so multiply those things. So we have 132.32 degree, and we have, you see, this is the sigma 1 towards the positive direction, sigma 2 because of, you see, it has a direct impact of this -1. So we can also calculate this sigma 2 here by like plotting these things. So this is my Mohr circle which has a radius of, right, from, if I am saying that this is P, so P to BC or P to AB, we have a Mohr circle radius, and you see by dropping those things, this is nothing but the tau xy, this is nothing but the tau xy, and you can simply get those things by sigma x plus sigma y by 2 here. So here you see, I mean to say that if you have these information sigma x, sigma y and tau xy, simply get the value of tau 1 and tau 2 here, and you see the theta. So again, by measuring those things, we can get these things, because you see the sigma 1 was towards the positive direction. So we have 56.5 mega Newton per meter square, that is in the tensile nature, and the sigma 2 which is, you see, towards the left direction of the horizon. So it is 106 mega Newton per meter square compressive, and theta 1 was pretty, like, because it was towards the clockwise direction. So we have from the BC, so it has a positive value 66.15 degree, and you see by adding 90 we have the theta 2 means the another location of the another principal plane. So 156.15 degree counterclockwise from the BC. So here you see, we need a paper on which you can simply plot the curve. Just by measuring those things, we can calculate those, we can get those values. So what is the salient features or the points of the Mohr circle is the compressive shear stress on the plane 90 degree apart from the circle are equal in the magnitude. That means it does not matter, like if you have a shear stress or complementary shear stress, either apart at the 90 degree or another plane of the 90 degree plus minus of the circle, they are equal. Second feature is the principal planes are always orthogonal, like you see either sigma 1 and sigma 2, they are always at the 90 degree to each other, they are orthogonal. So point L and M, whatever you see, the 2 points are there which we located, are always 180 degree apart from the circle, or we can say 1990 degree apart from the material side. There are no shear stress on principal planes as we discussed. So point L and M lie on the normal stress axis. Always you see, because we are talking about the principal planes only, so the principal planes doesn't contains any shear component is there. That means you see whatever the points are there, L and M, they are always lying on the normal stress axis. The planes of maximum shear are always at the 45 degree, from the principal point D and E, which are 90 degree. That means you see they are always exactly at 45 degree, and these two planes, the principal planes, are always containing the maximum shear stresses. And if you count both the part, then it is apart from the 90 degree, measured round from the circle from the points of L and M. The fifth point, the maximum shear stress are always equal in magnitude and given by D and E point, as we discussed in the previous graph. The normal stress on the plane of maximum shear stress, whatever the normal stress component is there, if you are talking about the maximum shear stress plane, the 45 degree, are always equal. That is the point D and E which we discussed in the point 5. Both have the normal stress coordinates which are equal to the principal stresses. That means you see, if you are talking about the maximum shear stresses, and if you are talking about the plane of that where these stresses are occurring, always we need to be very careful that actually what about the normal stress components are there about these planes, and they are always equal to two principal stresses. And you see, if you are talking about the principal planes or principal stresses, always we have to be very careful that actually there shouldn't be any normal stress component is there amongst those principal stresses or the principal planes. So now you see, as we know that this particular circle, the Mohr circle, was represented all the possible state of normal as well as the shear stress on any plane through a stress point in a material. Further, we have to see that the coordinates of point Q are seen to be same as those derived from the equilibrium elements in the the analytical solution, that is the normal as well as the shear components on any plane passing through the point can be found using Mohr circle. If it is passing from the center point where the coordinates are pretty symmetry, we can easily get any value of the normal as well as the shear stress from the Mohr circle itself. So now come to whatever we discussed these things, these points are there. We have, you see, this is tau, this is sigma, this is tau, and these whatever we discussed, all the salient features. Here you see this AB bar and BC bar, this is the P coordinate, and this is the first sigma 1, which is always coming from the first principal stresses, sigma 2 is the second principal stresses. So sigma 1 plus sigma 2 divided by 2 will give you the coordinate of the center point. So this is the center point. Then if you rotate this point, you see this q, then you will get, you see, like these points where this sigma x, this tau xy and this tau xy here is there. So here if you want to check the coordinate of AB bar, you have the two values of sigma y and tau xy. If you want to calculate the coordinate of BC bar, or if you have those things, you can simply plot those things, the sigma x and tau xy. So once you have these 2 points, like put those points here with those coordinates from these, you see you have sigma x, sigma y, tau xy. So put these 2 values here, fill up those things, get the value of sigma 1 and sigma 2, get the value of p. Once you have the p, then rotate these things, you see, by 2 theta, which will give you the principal plane. So you see now the principal plane is like that, you see earlier the straight one, now the principal plane is like that. So you see all the sides AB and BC of the element ABC, which are like 90 degree apart from each other, are always representing the circle, and they are always, you see, since 90 degrees, they are the total 180 degree apart from these things. So it has been like shown the Mohr circle represent all possible state of stress as we discussed. Thus it can be seen like that if you want to calculate the stress at a point, it can be easily calculated without any sort of calculation, just by measurement. Thus it can be seen the two planes IP and PM in the previous figure, they are always 180 degree apart on the diagram, and therefore 90 degree apart from the material side on which the shear stress tau theta is 0. That means you see the principal planes are there, and these planes are termed as the principal planes, and the normal stress acting on these are the principal stresses. Thus we can say that the sigma 1 is the first OL, sigma 2 is the total like the OM, and the center point is sigma 1 plus sigma y by 2, sigma 1 plus sigma 2 by 2. The maximum shear stress in an element is given by the top, always it is on the top of the circle, which is equal to the radius. So bottom of the points like top and bottom J1 and J2, thus the maximum shear stress would be sigma 1 minus sigma y by 2 equal to the radius of the, as I told you, the Mohr circle, which is equal to sigma 1 minus sigma y by 2, and the corresponding normal stress is obviously distance OP, that is sigma 1 plus sigma y by 2, that is the coordinate of the P, the center point. Further it can be seen that the planes on which the shear stress is maximum are situated 90 degree from the principal plane always. That means you can say the 45 degree from the material. If you want to calculate where the what is the maximum value and where it is exerting, it is always 90 degree from the principal plane where the maximum shear stresses are there, and you know that the principal planes are having 0 shear degree. So you see you can simply make those points just to make easy of the calculation. And then the minimum normal stress component, just the important, as you see it is simply the maximum part is there from the algebraic way. So the algebraic minimum stress could have a magnitude greater than that of the like the maximum principal stresses if the state of stress was such that the center of the circle is exactly left towards the origin. Means if it is going beyond certain things, then always you see we have sigma 1 which is a positive value, sigma 2 is always compressive, as we discussed in the previous case. So that is, you see here, if we are saying that the sigma 1 is 20 mega Newton per meter square, and if it is the sigma 2 which is the compressive nature, the principal stress another is minus 80 mega Newton per meter square. If these two values are there, let us assume, then tau maximum means the maximum shear stress is always left towards the origin. That means it has a value of 50 just by putting minus here, so 50 mega Newton per meter square. It should be noted that the principal stresses are considered a maximum or minimum mathematically. Just it's not the whatever the compressive or the negative stresses are there, negative stresses are there or the positive stresses are there, they are just giving you the feeling about whether it's a tensile or whether it's a compressive nature. Since the stresses are always perpendicular faces of any element which is given by the coordinates of two diametrically opposite points on the circle, they are always, you see, the sum of the two normal stresses for any, always sum of the two normal stresses sigma x and sigma y, or we can say sigma 1 plus sigma 2, and the orientation of the element is always constant. That means the sum of the invariant whatever you see the things are there for any particular state of stress, they are always giving you the feeling about the sigma 1, sigma 2, sigma x and sigma y. So you see here, which we can simply feeling about the two perpendicular normal stress components are there here, like these sigma y tau x y, sigma x tau x y, and the rotation of those things, and this is, you see, the sigma 1, this is the sigma 2, and you see these components are like that. So you see, like all those things which we discussed, which can easily understood from either you see the sigma x or sigma y are positive or negative, you see we can simply get. And if sigma 1 and sigma 2 are equal, the Mohs circle like dangers into a point, just you see it squeezes into the point and there is no shear stresses there which can be developed on xy plane. Means you see, if we can say that there is both principal stresses are equal, then you see what is the point is there, you see there is no shearing is there in that, and always whatever the things will come, they are coming in the xy plane. And the second case, if the sigma x plus sigma y is 0, means the total summation of both, the one is tensile, one is compressive, and the effect of the normal stress component 0, then the center of Mohs circle is coinciding exactly on the origin of exactly on the origin of sigma and tau coordinate. So we found that actually if both typical cases are there, then how to get the value of the extreme points sigma 1, sigma 2, or how to get the coordinates of those values about the circumference of the stress circle. Like you see, if the last case which we discussed about, that if if we have the tensile nature of stress, if we have the compression nature of stress, and if the summation is exactly and both are equal in the magnitude, then definitely you see the summation means the combined effect is 0 always, whatever the this center is there, because the center is nothing but the sigma x plus sigma y by 2. So center is always coming towards the point O. So P is coming towards the point O. So these are some of the special cases of the Mohs circle, and once we have the values of sigma x, sigma y, tau xy, we can easily plot those, you see this Mohs circle radius by keeping tau the one value on the circumference, that is sigma x and tau xy, another value is sigma x and tau xy, and once you have those values on the circle, you can simply draw the circle, because both are nothing but the diameter on the extreme corner of those things. And once you know the theta where it is they are exerting, you can simply measure the 2 theta, and this 2 theta, you see once you rotate that part from the sigma or tau, these things are simply by measuring those things, we have sigma 1, we have sigma 2, we have theta 1, we have theta 2, and theta 2 is nothing but equals to theta 1 plus 90. So it is, you see, this kind of exercises are pretty simple by measuring, there is no need to calculate. But there are certain drawbacks of this Mohs circle, as as I told you in my previous lecture also, that once if we have the value of sigma 1 or sigma 2 or tau xy are the absolute, like you see as we have discussed, like 10, 20, 30, 40, 50, all those things, then it is pretty easy to plot those curves here. But if we have the value of sigma 1 like 15.25 or 15.29, then you see again what we need to do, you need to again plot those things which is pretty again it is in the 2 or 3 digits, and then to make it out you need to round up those values, and once you round up those values, then whatever the angle is coming, this is not exactly accurate. So some sort of, you see, trial and error method is usable to plot those things, and always some sort of, we can say, a kind of errors are there in measuring those things. Or sometimes you see your thickness, whatever the pencil thickness is not proper, then always, or the scale is not correct, then always some sort of magnification error is there, or we can say this is not the correct way to resolve those stress components if we have, you see, this kind of stress nature. But if it is absolute value, there is no problem, you can straight away put the scale, get those values by measuring these components in the Mohs stress circle. So you see here in this lecture we discussed about the two different approaches which we discussed in the previous lectures, analytical approaches and the this graphical approach. In the graphical approach, again we discussed about that actually if we have the location of this theta 1 or theta 2, if theta 1 is negative, then how to go in the another way, and how to apart one by 180 degree by just giving positive value by adding 90 degree, and then by adding 90 degree to locate the another principal plane. Or if the theta 1 the principal plane location is positive, then there is no need to go in the positive direction, it is already in the feasible region, and then by adding 90 degree will give you the another location of the principal plane. So this is all about, you see, the stress components which we discussed in this lecture or in the previous lecture. Like actually if we have the different stresses are there, if they are inducing in a component either in the axial way, in the normal stress component, shear stress component, and if the combined effect is there, the interaction is there of these kind of stresses, then how to resolve the matter and how to get the maximum value of stress, normal stress, minimum value of normal stress, maximum value of the location, and what is the principal stress, what is the like the different stresses, and what is the these kind of maximum shear stresses are there, and what exactly the relation is there in between those normal as well as the shear stress components. So this is all about the stresses. In the next lecture, you see, now we are going to discuss about the strengths, okay, because you see, whenever the load application is there, we know that though the internal intensity of the resistances are there, and due to this the stresses are forming in the object, but there is a deformation, and when there is a deformation, there is a change of the shape of the material. And once you see, we are saying that there is a change of the shape of material, there is we need to measure that, and for measuring, you see, there is another technical term is there, that is the strain, that you see whether if you are pulling those things, then there is a pulling in one direction, but the compression is there on the other direction, means the tensile is there in one direction, x direction, but the compression is there in the another direction, then what exactly the relation is there in between this extension and the compression. So again, you see, we need to define some different parameters, and then you see in the next lecture we are going to discuss about that up to what extent we need to like pull the chain, or we can say the bar, or any kind of material, so that we can say that if you release those things, it is in the elastic nature, and once you see you are just pulling those things, and once you go beyond certain limit, you are in the plastic region, and then if you are working in the elastic region, then what the different coefficients are there, and once you go beyond certain region, then what the coefficients are there. So these, you see, the main terms are coming in the next lecture, that what is the strain, means how to measure the deformation, whether it's a tensile or like compressive, or in the shear formation. So all these types of strains which we are going to discuss, and then the other properties of the material. Thank you.